Welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it. This is Chapter 4, Section 3, so 4.3. And 4.3 is increasing and decreasing functions. Increasing and decreasing functions. And the first derivative test. All right. So first, let's start with a couple of definitions here. So definition. A function f is increasing, right, on an interval when for any two numbers x of 1 and x of 2 in the interval x of 1 being less than x of 2 implies that f of x of 1 is less than f of x of 2. All right. A function f is increasing on an interval when for any two numbers x of 1 and x of 2 in the interval x of 1 being less than x of 2 implies that f of x of 1 is less than f of x sub 2. So that's increasing. Now let's talk about decreasing, but it's a very similar definition. So I'm just going to change the pieces that are relevant. All right. So a function f of x, right? A function f is decreasing on an interval when for any two numbers x of 1 and x of 2 in the interval x of 1 being less than x of 2 implies that f of x of 1 is greater than f of x of 2. All right, so that's decreasing. And we have a third one here. So let's go ahead and write it. And again, it's very similar. But now we're going to say constant f of x is, a function f is constant on an interval when for any two numbers x of 1 and x of 2 in the interval x of 1 being less than x of 2 implies f of x of 1 is equal to f of x of 2. All right. So let's get a visual as to what we're talking about here. So let's say that I had, well, the following function. All right, something that looked like that. In the first definition for increasing, we're talking about something like this. Let's say that here is x of 1, and here is x of 2. All right. And we're saying, well, x of 1 is less than x of 2, right? And f of x of 1 is less than f of x of 2. So in here, if we look at the tangent line here, or near here in any of this region, you would notice that from left to right, it is going up. In the second definition for decreasing, right, we've got something like this. Let's say here's x of 1, here's x of 2. And throughout this entire interval, right, well, we have x of 1 is less than x of 2, but f of x of 1 is greater than f of x of 2. And notice that in here, the tangent lines are going down, right? And lastly, in the third scenario, let's say that's x sub 1, and that is x sub 2. So in here, it is constant if they are at the same height. And what you notice here is that our tangent line is horizontal, right? They're at the same height. So visually, that's what we're talking about. This is decreasing, this is constant, this is increasing, all right? So essentially, if the tangent lines are going from left to right, if they're going down, the function is decreasing. If the tangent lines are staying at the same height, the function is constant. And if the tangent lines are going from left to right, if they're going up, they're increasing. Now, that's just the definition. Now let's get a theorem about how to tell, without actually having to look at the graph, how to tell where something is increasing or decreasing. Theorem. So this is a test for increasing and decreasing functions. All right. Let f be a function that is continuous on the closed interval AB and differentiable on the open interval AB, right? So the first part of this test says if f prime of x is greater than 0 for all x in the open interval from A to B, then f is increasing on that interval, on that closed interval. All right. The next definition, very similar. If f prime of x is less than 0 for all x in the open interval, then f is decreasing on that interval. And lastly, if f prime of x is equal to 0 for all x in the interval, then f is constant on that interval. All right. So now, noticing here what we're saying, f prime is greater than 0, f prime less than 0, f prime equals 0. What we're essentially doing here is we're comparing things to f prime, right? The derivative. So visually speaking, what are we saying? We're comparing things to the tangent lines, all right? So we're essentially just looking at what the tangent lines are doing to see overall what the function is doing, right? Because remember, these are slopes of tangent lines. All right, so now let's do an example. Identify the open interval or intervals on which the function is increasing or decreasing. All right, so here we go. Let's say that I have this function. F of x is equal to 12x minus x cubed. All right. Well, what are we going to do? Well, essentially, I'm going to do what this is telling us. All right, we're going to look for when the derivative is positive, when it is negative, all right, to figure out when it's increasing or decreasing. So take the derivative. F prime of x is equal to 12 minus 3x squared. All right. Now, how do we use that to figure out where it might be increasing or decreasing? Well, the trick here is hidden in this part, right? And f prime of x equals 0. The reason for that is because, well, if we're going up, if we're increasing, and then at some point we're decreasing, well, somewhere in the middle, it must have been 0, right? We went from positive to negative. Somewhere in the middle, we must have hit 0. So what we're going to do here is look for where that 0 is. So we're going to say, well, let this thing, 12 minus 3x squared, be equal to 0. Solving for x, well, x squared would be move the 12 over, divide by -3. So x squared is equal to +4. Therefore, x is equal to plus or minus 2. Now, what this essentially does, it gives us test points. All right, this is telling us where the function has a horizontal tangent line. Well, what we can do is test around that to see what we would get. All right, and what we're going to do is we're going to test it into the derivative. All right, and well, let's see, what can we use? In general, the three easiest values to test are 0, 1, and -1 in that order. So whenever possible, use those. So in here, between -2 and 2, I'm going to use 0 as my test point. Above 2, I'll use 3, and below -2, I'll use -3. And what we care about here is the sign, right? So let's go ahead and see what happens. If I plug in -3, well, what do I get here? -3 squared is 9. 3 times 9 is 27. 12 minus 27, all we care about is the sign. 12 minus 27 is negative. So in here, I'm going to say that in this region, we've got a negative tangent slopes. In the next part, plug in 0. 0 squared is 0. 0 times 3 is 0. 12 minus 0 is 12. So 12 is a positive value. So here, where we've got positive tangent slopes. And in the last one, plug in 3. 3 squared, 9. 9 times 3 is 27. 12 minus 27, again, we end up with a negative value. So essentially here is what we get is that in here, we're decreasing, in here, we're increasing, and over here, we're decreasing again. So as far as the intervals go, to answer the actual question, we've got that it is decreasing on the interval from -infinity to -2, not including -2, right? Because at -2, we found that the tangent slope was 0. So it's not increasing or decreasing. And then again, from 2 to infinity. That's where it would be decreasing. As far as increasing, well, in this region, from -2 to 2. All right. Now, just to give you a visual as to what we found here, and the visual is not necessarily, it's not at all required, at this point at least. This is what this function looks like. All right. Something like this. Right. And the points 2 and -2, well, they were where we have horizontal tangent lines right here. And what we found here is that, well, for every value less than -2, we had decreasing. Well, that makes sense. We have negative tangent lines there. For all the values between -2 and 2, we've got increasing. It makes sense. We've got positive tangent lines. And everything above 2, we've got decreasing again, which again makes sense. We've got negative tangent lines. And by that I mean the slopes, right? All right, so in here, we essentially did what's called the first derivative test. All right, so let's actually talk about explicitly about that first derivative test. So theorem. And this is called the first derivative test. Let C be a critical value of a function f that is continuous on some open interval, on an open interval I, containing C. Right? If f is differentiable at C, excuse me, let me rephrase that. If f is differentiable on the interval, except possibly at C itself, then f of C can be classified as follows. And here f of C being the actual point, right? The critical value. If f prime of x changes from negative to positive at C, then f has a relative minimum at that point, C comma f of C. All right. Similarly, if f prime of x changes from positive to negative at C, then f has a relative max at C comma f of C. I guess I could have just done this. And lastly, if f prime of x does not change sign at C, in other words, we're going from positive to positive or negative to negative, all right, then f of C is neither a relative minimum nor a relative max. All right. So what are we saying there? Let's look at some scenarios. That first scenario, if f prime of x changes from negative to positive, then it has a relative minimum. So let's see what that looks like. We've got this function. Yeah, let's draw that better. There we go. And let's say that here is C. This point right here is at the height of f of C. And notice that in here, we're going from negative tangent slopes to positive tangent slopes. So in other words, we're going from f prime of x being negative to positive at that value. So in here, this is a relative minimum. All right. Now let's look at the next scenario. Here. And again, notice that at these points, we've got horizontal tangent lines, right? At this point, I would have this horizontal tangent line. This point here being at the value of C, comma, f of C. And in here, we're going from positive tangent slopes to negative tangent slopes. All right. We're going from positive tangent slopes to negative tangent slopes, making this right here, by definition, relative max. Right. From positive to negative tangent slopes. And all right, so that's relative minimum, relative max. Now let's look at that third scenario there. If it does not change in sign, then that point is neither a min nor a max. Okay, so what does a visual there look like? Well, it could be something like this. All right, where at this point, so now let me actually make that a little bit clearer. What's happening there? All right, so at this point here, we've got a horizontal tangent line, but we're going from increasing to increasing. All right, Similarly, we can draw the opposite scenario where we've got something like this, right? And again, at that point here, horizontal tangent line, but we're going from decreasing to decreasing, all right? So in neither of these scenarios do we have a relative min nor a max, right? So this is neither. So let's see what we can do here. This is the first derivative test, all right? So essentially what it does, it allows us to classify where a minimum and a maximum would be. So let's do some examples. Identify the extrema. Identify all relative extrema. All right, so let's say that I have this function. F of x is equal to 2x cubed plus 3x squared minus 12x. All right. So, well, what do we need to do? Based on this idea, right? Well, we first have to figure out where we have a critical value, right? Once we figure out where the critical value is, well, we can test around it to see we have negative to positive, positive to negative, or no change in that, all right, at those critical values. So let's figure out where the critical points are here. So we're going to start by finding the critical points, which, if you recall, is where f prime of x is equal to 0 or undefined. So, all right, let's find f prime of x. F prime is equal to 6x squared plus 6x minus 12. And I'm going to set that equal to 0. Notice here that I can divide both sides by 6, giving me x squared plus x minus 2 is equal to 0. And I can factor this to say x plus 2 times x minus 1 is equal to 0, giving me the critical values of x equals negative 2 and x equals 1. All right. So at this point, let's see what we have. We need to test around these 2 points. So here's negative 2, here's 1, and we're going to test them into our derivative function, right? The derivative. So let's go ahead and test some things out. Now, in general, we can go off of the factored version, assuming that you didn't move anything to the other side, because what we're looking for here is the sign, right? In other words, what I'm getting at here is that f prime of x is equivalent to saying 6 times x plus 2 times x minus 2, and we could just test it into here. So I'm going to use, well, what values? I'm going to use 0 here, I'm going to use 2 here, and I'm going to use negative 3 there, right? And let's see what happens. When I plug in negative 3, remember, all I care about is the sign. This 6, well, that 6 is always positive, irrelevant of what I plug in. Plug in negative 3. So in here, we're figuring out what happens when x equals negative 3. Negative 3 plus 2, that's negative. Negative 3 minus 2, that's negative again. Overall, positive times a negative is a positive. So in here, we've got a positive region giving us that we're increasing there. Let's test out 0. If I plug in 0, well, what do I get? Well, that 6 again is positive. 0 plus 2 is positive. 0 minus 2 is negative. So overall, positive times a positive times 1 negative is negative. So in here, we're decreasing. And if x equals 2, well, what do we have? Again, that 6 is just positive. X plus 2. Well, 2 plus 2 is positive. 2 minus 2. Oh, sorry, I copied that wrong. Minus 1, look at that. The rest, these other values would have held still, right? If I plug in negative 3 minus 1 is still negative. 0 minus 1 is still negative. But now 2 minus 1 is positive. So overall here, I get positive, meaning that here I've got an increasing region again. All right. So what does that tell us? Well, look at this. We're going from positive to negative. So in here, by definition, we've got a relative max. And here we're going from negative to positive. So in here, by definition, we have a relative minimum. All right. And this should sort of make sense, right? Because in here, if we got increasing, then decreasing, then increasing, yeah, there's our max, there's our min, right? I'll draw that better in a second. But what we have to say now is that we have a relative maximum at the point -2 comma 20. How did I get that 20? I plugged it into here. -2 cubed is -8 times 2, -16. -2 squared is 4 times 3 is 12. -16 plus 12 is -4. And then -12 times -2 is -24. And over here, excuse me, positive 24. And then we had -20 plus 24. No, -4 plus 24. We get 20. All right. Now, by similar reasoning, we end up with a relative minimum at the point 1 comma -7. Right? 2 plus 3 is 5. 5 minus 12 is -7. So to get a full visual as to what we found here, this is what we've got. Our function looks like this. Right? Something like that. In here, we've got that at -2, we've got a height of 20. And at 1, we had a height of -7. All right. So that's what we found there. And again, increasing, decreasing, increasing. All right, next example. C. Let's say that our function f of x was x squared over x squared minus 9. All right. Now in here, there's various ways to do this, right? I'm gonna find the derivative using the quotient rule. So the derivative of the top, 2x, times the bottom, minus the derivative of the bottom, times the top, all over the bottom squared. All right. Now, simplifying this a little bit, well, what do we get? Distribute out this 2x, so I have 2x cubed minus 18x minus 2x cubed, all of this over x squared minus 9 squared. And at that point, what do we actually have? Well, in here, 2x cubed minus 2x cubed goes away, so I just get -18x over x squared minus 9 squared. All right. But before I continue there, notice that the domain for this is x cannot be equal to plus or minus 3. All right. So plus or minus 3 is undefined for the function. Coincidentally, it's also undefined for f prime of x. Well, not necessarily coincidentally. If it's not in the domain of f, it shouldn't be in the domain of f prime. All right. Now, but what do we do with this? What are we going to say? Let's find our critical values, right? Which is what we were doing here. Perhaps I should make it clear here that we were finding critical values, right, or critical points. And the critical points, again, are where f prime of x is equal to 0 or undefined. But when it's undefined, it still needs to be in the domain. So essentially what we get here is, well, first let's set this equal to 0. -18x over x squared minus 9 squared. And set it equal to 0. I've got a fraction equaling 0. The only possible way for a fraction to equal 0 is if the numerator itself is equal to 0. At that point, divide both sides by -18 and I get that x equals 0. But we also need to test around our domain. We cannot be plugging in positive or -3, right? So what this gives us now is that if this is our interval and we're going to test into f prime of x, we need to test around 0, but also around -3 and +3, since those are not in our domain. And, well, what am I going to use? To the left of -3, I'll use -4. Between -3 and 0, I'll use -1. Between 0 and 3, I'll use 1. And then I'll use 4 to the right of 3. And we're plugging this into the first derivative. Notice here that, well, let's look at this first derivative, right? This was our first derivative. Notice that in the bottom, as long as I'm not plugging in 3 or -3, overall, this is going to be positive, right? This is always going to be positive because I'm squaring it. So I don't really have to worry about what's going on in the denominator. It's always positive. So let's figure out the numerator, what the numerator is doing. So I have -18 times -4. Negative times a negative is positive. So there we're increasing. Plug in -1. -18 times -1, increasing again. Plug in 1. -18 times 1, that's negative. So now we're decreasing. And perhaps I should have said here that we were still increasing. Now we're decreasing. Plug in 4. -18 times 4, that's negative. So we're decreasing still. So in here, we've only got one place where this is either a minimum or a maximum, and that's here. There's a relative max. And it's a maximum because we went from increasing to decreasing. All right. Now, let's see what this function actually looks like. So it happens to have vertical asymptotes at -3 and at 3. And it looks like this. All right. It also has this horizontal asymptote of 0. All right. And let's compare it to what we found here. From -infinity to -3, -infinity to -3, it is increasing. From -3 to 0, increasing still. From 0 to -3, decreasing. And then from 3 beyond, decreasing still. So in here, this point right here, that was our maximum, right? Right there. Notice here that we needed to test around this vertical asymptote and this one as well, right? But again, that's because it's not part of our domain, so we must always test around our domain as well as our critical values. All right, let's do another one. That was C. D. Let's say I had f of x being equal to e to the 2x over e to the 2x plus 1. All right. And again, well, we're looking for where this could have a relative max or a min. So let's start with that. So actually, before that, let's just go ahead and look for the domain first. So the domain is e to the 2x plus 1 cannot be equal to 0. Right? Move that over. So e to the 2x cannot be equal to -1. Well, look at that. In here, we have an e to the 2x, right? And essentially, I can rewrite this as saying e to the x squared cannot be equal to -1. Well, yeah, as long as we're staying within real values, that's impossible, right? Because in here, e to the x irrelevant of what the values are there, when we square them, overall, it's positive. It turns out e to the x is always positive, right? But overall here, when I square them, it's positive. A positive can't be equal to a negative. Well, yeah, of course, that's true. Positive values cannot be equal to negatives. So the domain here ends up being all real numbers. So the domain is all real numbers. All right, so we don't really have to worry about testing around the domain like we did in the previous example. So what I need to do now is, well, let's just go ahead and find the derivative. So f prime of x would be the derivative of the top, 2e to the 2x, times the bottom, e to the 2x plus 1, minus the derivative of the bottom, 2e to the 2x, times the top, e to the 2x. All of this over the bottom, e to the 2x plus 1 squared. All right, so let's see what we have here. I see a 2e to the 2x in both of these, so let's go ahead and factor that out. 2e to the 2x times, what are we left with? We're left with e to the x plus, e to the 2x plus 1 minus e to the 2x. All of this over e to the 2x plus 1 squared. In here, these parentheses aren't doing anything here, so e to the 2x minus e to the 2x cancel each other out, and we still have this 1 here, so we get 1 times 2 is 2, so 2e to the 2x over e to the 2x plus 1 squared. Now, since we were looking for critical points, right, and that was where f prime of x is equal to 0 or undefined, well, let's set this equal to 0. 2e to the 2x over e to the 2x plus 1 squared equaling 0. I've got a fraction equaling 0. The only way for that to happen is if the numerator itself is equal to 0. And, well, in here, divide both sides by 2. E to the 2x is equal to 0. Take ln of both sides. 2x is equal to ln of 0. But ln of 0 is undefined. So what does that tell us? Well, that tells us that there are no critical values. All right, there's no critical values. So what now? Well, so let's see. Here I just said that there's no critical points, no critical values. All right. What does that mean? Well, what that tells us, when we have no critical points or critical values, it tells us that there's no change in increasing, decreasing. What do I mean? That means that overall, it's either always increasing or always decreasing throughout its entire domain. So when that happens, well, how do we test it? Well, we can test any value that we want in our domain. So, for example, we can test 0. So let's figure out what f prime of 0 does. And remember, this is our derivative, so I have 2e to the 2 times 0 over e to the 2 times 0 plus 1 squared. 0 times 2 is 0, e to the 0 is 1, 2 times 1 is 2, over 1 plus 1 squared, right? Giving me, well, 1 plus 1 is 2, 2 squared is 4, 2 over 4 is 1 half. Now 1 half is greater than 0, right? So what this tells us now is that the tangent slopes are all positive throughout the entire domain, so it is increasing everywhere. Let's just say increasing everywhere. All right. Now, let's see what this function looks like. So I had e to the 2x over e to the 2x plus 1. So it looks like this. It has two horizontal asymptotes, right? And essentially the function looks as follows. All right. Notice that nowhere would this have a horizontal tangent line, right? And so because of that, it would have no critical values, all right? So it's increasing everywhere throughout the entire domain is going up. Even though over here it's less up, it's still up, right? It still has positive tangent slopes there. All right, now let's do a next example. But before that, I'm going to introduce slightly different instructions. So I'm going to say consider. Actually, you know what? I have an easier way to phrase this. So same instructions. But we've got f of x being equal to x over 2 plus cosine of x. But we're going to strictly work between 0 and 2 pi. All right. So, all right. So in here, what do? Well, the same thing as we did in the other examples, which is start by finding the critical values. So critical points. That's where f prime of x is equal to 0 or undefined. So what's my derivative here? Well, f prime of x would be 1/2 plus the derivative of cosine is negative sine, so minus sine of x. And if I set this equal to 0, then what I get here is sine of x is equal to 1/2, right? Which tells me then that x on this interval from 0 to 2 pi, well, essentially that tells us we're working within the unit circle. So we're in the unit circle. Where is sine equal to 1/2? Well, it happens at pi over 6 and at 5 pi over 6. So that's the values that we need to test around. So let's see. In here, this is around, we're testing around f prime. Here's pi over 6. Here's 5 pi over 6, right? And what can we test? Well, 0 is part of our interval, so we can use 0 to the left of pi over 6. Between pi over 6 and 5 pi over 6, we can use, well, pi over 2. And then to the right of 5 pi over 6, we can use pi, right? And let's see what do we get here. When I plug in 0 into my first derivative, sine of 0 is 0. 1/2 minus 0 is 1/2, which is positive. When I plug in pi over 2, sine of pi over 2, well, sine of pi over 2 is 1. 1/2 minus 1 is negative 1/2, so we get negative. Plug in pi. Sine of pi is 0. 1/2 minus 0 is 1/2. So again, we end up with a positive value. So what we found here is we're going from increasing to decreasing to increasing. And these values, pi over 6 and 5 pi over 6, are definitely in the domain here. So what we have is a relative max here and a relative min over here. All right. So we can say here we have increasing on, well, on what interval here? We're going to say from 0 to pi over 6. And really this should be an open interval, but that's fine. From 0 to pi over 6, union 5 pi over 6 and beyond. But beyond here means up to 2 pi. And for decreasing, well, just in this region, from pi over 6 to 5 pi over 6. All right. Now let's get a visual to this so you can see essentially what we found. And I'm going to focus essentially or mostly on the interval from 0 to 2 pi. but this is what the function looks like. Something like that. Let's try to draw that a little bit better. Right? And in here, we're working between 0 and 2 pi. And we found that we had a relative max at pi over 6. So this value right here is at pi over 6. And the minimum, this value over here, at 5 pi over 6. All right? So there we go. And in here, increasing slopes. In this region, decreasing slopes. Continuing on there, increasing slopes. All right. So that was E. F. Let's say that f of x was sine of x plus cosine of x, and we'll again just focus on the interval between 0 and 2 pi. All right, so we're looking for relative min and max. We're looking for the behavior here, so we're going to figure out what are the critical points, and that's where f prime of x is equal to 0 or undefined. Normally, the domain for this function is all real numbers, right? So the fact that we're restricting it between 0 and 2 pi does not affect that in the sense of where we're going to have an undefined case, right? There's not going to be any vertical asymptotes here. So f prime of x, we're going to say, well, the derivative of sine is cosine. The derivative of cosine is negative sine. All right. The next thing we need to do is set these two equal to each other. This means set these two equal to 0, which means that we need to set them equal to each other. And on the unit circle, right, between 0 and 2 pi, where is cosine of x equal to sine of x? That's what this is asking. Well, where they're equal would be at pi over 4 and also at 5 pi over 4, right? And again, that's from the unit circle. At pi over 4, they're both radical 2 over 2. At 5 pi over 4, they're both negative radical 2 over 2. So now, applying the first derivative test, now we're plugging things into the first derivative. We're going to check what happens to the left of pi over 4, between pi over 4 and 5 pi over 4, and to the right of that. To the left of pi over 4, well, we could do something like, well, we could use 0 if we want to. Yeah, I guess I'll use 0. Between pi over 4 and 5 pi over 4. The easy ones here would be pi over 2 or pi. I'm going to go with pi. Above 5 pi over 4, but below 2 pi. Above 5 pi over 4, well, 5 pi over 4 is in the third quadrant. So I can use something like 3 pi over 2 to be exactly on the axis, right, of the unit circle I'm talking about. So let's see what happens. When I plug in 0, what do I get? Cosine of 0 is 1. Sine of 0 is 0. 1 minus 0, positive. Plug in pi. Cosine of pi, negative 1. Sine of pi, 0. Negative 1 minus 0 is negative. Plug in 3 pi over 2. Cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2, negative 1. 0 minus negative 1, that's 0 plus 1. In other words, a positive value. So we get it's increasing, then decreasing, and then increasing again. Given us here, we have a relative max. And here we've got a relative min. All right. Visually speaking, or excuse me, we can also say that the interval of increasing would be between 0 and pi over 4. And then again, from 5 pi over 4 to 2 pi, right? Because we were stopping this at 2 pi. And then as far as decreasing goes, we're just in this region between pi over 4 and 5 pi over 4. Now let's get a visual as to what we found. And the function here looks something similar to this. All right, where in here, this value is, this x value is 0, and we're going all the way up to 2 pi. That's around here, 2 pi. And we found that we've got here, at this point, at pi over 4, we've got our max, and that 5 pi over 4, we've got our minimum. All right. And in this region, increasing, then decreasing, and then again increasing. So there you go. That's what we get there. All right, that concludes 4.3. And again, this was just using the first derivative to figure out where the relative max and min values are. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.